Discussion of the n equals 4 theory. N equals 4 theory will really be in the background of much of the discussion. Today's class will be dedicated to the study of monopoles and their properties. Okay, so fine. So just to be concrete and to follow the notation of this review that I recommended to you last class, we will focus on SU2 gauge theories. Much of what I say, though, generalizes very easily to SU and gauge theories because SU and gauge theories have SU2 subgroups, and everything I say can be embedded into an SU2 subgroup. Okay, but just to be concrete, we will focus on SU2 gauge theories. And let's start really slow. Let us consider an SU2 gauge theory whose Lagrangian is given by trace f square plus d mu phi square, where phi plus v of phi, let's say. Where phi is an adjoint field. So that's in the 3 of SU2. It's like a vector of SU3. Okay, several times in these lectures, and outside these lectures, you know all this well, we've referred to this model to describe monopoles. In today's lecture, we're going to do it more carefully with equations. Okay, so we will sometimes to match. This is a normalization of Lagrangians that I like. It's not the normalization that Harvey adopts. Okay. Firstly, he calls this GE. Okay, let's though it hurts me to do this, I'll write this as 1 by E square. And secondly, he works with a field normalization such that our phi is equal to phi Harvey times E. And our A is equal to A Harvey times E. Okay? And with this normalization, his Lagrangian becomes TRF H square plus D mu phi H square without the 1 by E square plus V tilde phi H. Okay. Now the nice thing about our normalization, just to get these things out of the way, the nice thing about our normalization of gauge fields was that up to factors of plus minus, d mu in our normalization was d mu plus I a mu. Let's say I a mu commutator. It was acting on adjoint fields. Okay. This is for us. For Harvey, d mu is equal to d mu plus, it's the same covariant derivative, but then he has to plug in that our gauge field is his gauge field times E. Okay, so plus I E a mu H. Okay, and there's a similar issue with the webs of fields, which we'll come to at some point. Okay, so this. Okay, we will largely work in Harvey's notation and drop the symbol H. Please ask me if you're confused about which convention we're working. Okay, fine. So, for concreteness, we suppose that there is some potential. We don't really care where that potential is. But we will suppose that it has this V of phi. It's a gauge invariant potential. Okay, so it's really V of phi square. Right, it's V of the vector phi square, or if you want, trace phi square. Okay, and this potential we will take to have a minimum at phi square equals V square. Okay, so this trace phi square is up to some factor of order 1, same as the length of the vector in SO3 normalization square. Okay, so the length of the vector is V, up to factors of order 2, which are all very carefully worked out in Hubby's lecture, also I won't deep dive very carefully. Okay, so now let me remind you of this discussion that we've had many times about monopoles. But let me remind you about it in slightly more quantitative terms. Okay, we've got this Lagrangian which has a potential, let us suppose, and that potential demands that our scalar field, potential is minimized. Let's say it's 0, it doesn't really matter for a while. It's minimized, yeah, but let's say it's 0, Okay, it doesn't matter. Let's say it's 0. That it's minimized when this vector V has a particular length. Now, we're going to search for solutions of this theory. In that solution, this vector V can be whatever it is. But when we go to infinity, this vector V had better approach this length. Okay? Because we don't want an energy density over an infinite volume, because that would be infinite energy. So at infinity, V must reach its vacuum configuration, its lowest energy configuration, clearly. This clear?
You see, this is just the value of infinity.
No, infinity.
Just infinity.
Just infinity. In the middle, it can do what it wants.
Equations of motion
Will determine what it is. But if we want to look for finite energy solutions, at infinity, trace phi must go to V square. Okay? Now, because trace phi goes to V square at infinity, we've got options. The simplest thing the field can do is go to some value of V, let's say in the 3 direction, SU to 3 direction, and stay there forever. And actually, the simplest thing it could do is to be there forever for over all space, not just at infinity. This will give us the vacuum solution. A is equal to 0, V is a constant on the vacuum manifold and not changing. Clearly, this is the vacuum solution. You can't get lower energy than this. That's clear, right? But we might want to look for solutions that are not vacuum. And we'll see in what sense they're special in just a minute. Okay? So in these solutions, all we demand is that V reaches this vacuum manifold at infinity. Now the vacuum manifold at infinity is an S2, because we've got a vector, SO3 vector of a certain length, but it can point in any direction. This is clear, right? Okay. However, infinity in space, we're looking at static solutions. So we're just looking at space. So space is R3, infinity of R3 is also an S2. So we've got a map from S2 to S2. Okay? Maps can be trivial, like that was for the vacuum, but could also be non-trivial. So we could have winding. Okay? So maps, so finite energy solutions are labeled by an integer, which are maps from S2 to winding of S2 to S2. We've discussed this on many occasions in the past, but is this clear? Okay? Now, suppose I specify a particular winding. Clearly, the space of field configurations breaks up into configurations labeled by winding. Okay? Since in classical evolution, actually also quantum mechanically, but at least in classical evolution. This winding number cannot change discretely. Cannot change suddenly in a continuous way. It's a discrete number. It's going to be conserved. Okay? So while we've already discussed what the vacuum solution of this theory is, there is a more interesting gradation of this question. What is the vacuum solution? What are the vacuum solutions, maybe, for any given winding number? Okay? It may be higher energy than the vacuum, but because it's got the conserved charge protecting it, it cannot decay to the vacuum. Okay? So this is an interesting question that we could ask. Okay. Now, the first thing you might think of is if I was looking for, let's try to look for solutions at winding number 1 to start with. The first thing you could think of is, if I was looking for such a solution, I'm forced to have winding because the field is forced to wind. But if I want to get the lowest energy, maybe I should turn the gauge field to 0. This is wrong, but it's not an unnatural thing to first say. Okay? Now let's explain why this is wrong. This quantity, there is an energy cost. Winding carries an energy cost. Okay? What is that energy cost? It comes from the fact that there is a derivative. Okay? Let's estimate how that energy goes. Suppose I've got phi and it's winding over, so phi is some vector of modulus of E, and it's got some direction n hat in group space. Okay? Now that n hat has to wind on a sphere of radius r. Because n hat is some, its angle changes more or less by 2 pi, some order 1 number as you go around in order for it to wind. It's clear that the derivative of phi, okay, it's clear that the derivative of phi on a sphere of radius r is of order 1 by r. Right? Because over a distance of order r, something has to change by something of order 1. This clear? In the angular directions. In the radial direction, there is no derivative. Because the field phi has reached somewhere on the vacuum manifold and is staying there forever at r equals infinity. That's why there's a hope of having finite energy density. Okay, so let's assume that basically phi only changes in angular direction. It stays fixed in radial direction for r large enough. That was our hope to get a finite energy density. Okay? However, so del phi is 1 by r. Okay? So therefore del phi, the whole thing squared, it goes like 1 by r squared. Now the energy contains del phi square from the Lagrangian. Okay? So the energy is of order dr, r squared, because of the measure factor in 3 dimensions, by r squared. And so is linearly divergent. So it goes like r, where r is the size of our infinity sphere. So you see, even though we tried to get this solution to look like it was zero energy, we failed. Okay? Because even though the radial derivative, even though the potential energy was zero, the potential energy coming from V, the potential energy coming from gradients of phi field gave us infinity if there was widening. This tells us that if we had not a gauge theory, just a theory in which the SU2 was a global symmetry, and we were trying to understand what the configurations in this theory are, there are no interesting winding configurations.
So I would normally expect delta phi to be mod V times whatever is the change in n hat.
Mod what?
Mod V, the Weber frequency.
Yes.
Times change in the normal.
Correct. So delta phi, as you say, will be proportional to V. Okay, so now I've got the sphere. The normal vector is changing from here to here. Length of this is order r. Change in the vectors order v times 1. You're right, there's a v here. There would be a v square. Okay, so this would also have a v square. But the point is that the r dependence is what kills you. Okay, all good? So these winding configurations, they look very attractive, but this attractiveness looks like it would have been there in a scalar theory without gauge fields also. But it's a fake. These configurations don't exist. They're always infinite energy. By the way, this analysis we could do in 2 dimensions. We could repeat this analysis in 2 dimensions, and then we would get r dr by r squared. And this would give you a log r. And this is the famous IR divergence of vortices in 2 dimensions. And this log r looks like it kills them, but at finite temperature they can proliferate, because the entropy of these vortices also go like log r. Okay? So there's an interesting story associated with these configurations, are not, because the log is so weak, these configurations are not quite killed in 2 dimensions. Okay, in 3 dimensions is pretty bad. Is this clear? Okay, but so far we've been pretending that these configurations here, that these configurations are just in an ungauged theory. Now the whole point of a gauge theory is that the derivative of fields changes. Right? The whole point of a gauge theory is that the derivative of fields changes. That we don't have covariant derivatives, not the ordinary derivative. So perhaps we can do better by turning on a gauge field.
Is this related to Derrick's theorem?
Derrick's theorem. Yeah, Derrick's theorem was some, let's see, remind me, Derrick's theorem said there were no solitons in scalar theories?
Yes.
Yeah. Yeah. Let us see if we can prove Derrick's theorem. I'll have to check. Let's see. So Karthik is saying there's this theorem which tells us that in theory of purely scalar fields, there are no solitonic solutions in some dimension or higher. Right? Let's see if we can prove this theorem, and then we'll see if what my vague memory is that it came from some scaling. So let's see. So suppose we've got a theory which is del phi the whole thing squared plus v of phi. And suppose you give me a solution from phi naught of x, which you claim solves the equations. Okay. Now I want to prove that this is impossible. And I think the way to work goes as follows. I'm not sure I'm going to get it. Just give me 1 minute. Let's see if I can. There was scaling involved in this theorem. I think we were supposed to look for the solution which went like
stable web. So you need some stable web here. So you need to have a solution where if you rescale the thing, it does not go to a lower
energy. Exactly. So let's look for solutions which are of the form like this. Okay. If it's a solution, it should be stationary, in particular under variations of lambda and a. Okay. Now let us look at the a. Let's start by looking at the a dependence of each of these 2 terms. This term's a dependence goes like a to the power d minus 2. D is the number of dimensions whereas this term's A dependence goes like A to the power D. Now, therefore, the way that this could work is how? This is the point, right? Let's say you've got some finite energy. Now, if D is greater than 2, no matter what that finite energy is, if it's a positive number, let me also suppose V is everywhere positive. V is everywhere positive and D is greater than 2. So both these configure, both the kinetic and the potential term are positive. Right. Now, by scaling A, I decrease or increase both of these. So it's impossible for them to play off against each other. Okay, that was the theorem. Now there may have been more, but roughly this is how the theorem went, right? Okay, so we already see very simply that there could not be a solution. Okay, I suppose, the danger is, right, this theorem, now let's check whether this theorem wants you to go bigger or smaller. I think it wants you to go smaller.
What is the condition on V on phi here?
Let's suppose V of phi is any function that is everywhere positive.
Basically, coming just from D integral.
What?
D.
Yeah, integral d dx.
V of phi must be a marginal operator or something, right? To get this condition.
No. Yeah, I've just switched lambda off. Let me just look at this. Let me just look at this. Suppose suppose I plug lambda into this object, and I get some number. So suppose E of phi naught is equal to some E. Okay, let's suppose that K is equal to K1 and V is equal to V1, V of this phi naught. Now, when we do this A, we're going to get A to the power K1 to the power D minus 2 plus A to the power D times V1. Since these are both positive and in D greater than 2 the powers are also positive, it's impossible for that to be stationary condition for variation with respect to A. It's a monotonic function in A. Okay? Now the condition, however, it might have been that there were finite energy configurations whose minimum size was 0. And then they would be stabilized by some quantum effects. What we are saying here is even more. Doesn't matter what happens in the UV. IR forbids these configurations. Okay? So we weren't even really talking about solutions. We're just talking about winding configurations. So it's a bit different from Derrick's theorem. Derrick's theorem was really about question of existence of solutions. We've just argued that even winding configurations don't exist. Scalar theory. But maybe there's some better connection. Okay, excellent. This argument won't work for D equals 1, and in fact that's good because there are solitons in D. Actually, exactly. D here, by the way, was spatial dimension because I was looking at energy. Okay, so it will not work for D equals 1, and right, exactly, and the sine-Gordon soliton is a solution. Counter example there. But for D greater than 3, it's definitely greater than equal to 3, it's definitely true.
Equal to 2
is also true. Okay, yeah, perfect. Okay, excellent, yeah. It's a very simple theorem, as you see, but very powerful, right? It makes an immediate powerful statement. Okay. Okay, fine. So, but let's get back to where we were. We were talking about how we had this infinity because we had this derivative of the field being too large in the angular directions. Now, can we try to turn on gauge fields? Can we try to turn on gauge fields that ameliorates this problem? Now, at first sight, you might think, well, okay, maybe we can get the covariant derivative to be 0, or smaller by turning on gauge field, but then we'll turn on an if square term. So, you'll jump from the frying pan into the fire. That's what you might at first think. But if you think a little more, you'll see that's not the case. Why is it not the case? You see, what we had was a derivative that was taking you from one vacuum configuration to another. Now, these vacuum configurations were gauge equivalent, because you can go from any one point on the vacuum manifold to any other point on the vacuum manifold by algebraically gauge equivalent, not physically. Physically, because it's large gauge transformation. But algebraically, you could go from one point on the vacuum manifold to another by an SU2 gauge transformation, SU2 rotation. Right? Okay? However, therefore, the kind of gauge field you will need to get rid of this derivative can be obtained this way. Write this vacuum manifold as phi naught, let's say phi pointing in the 3 direction, times the rotation needed to take you here. So you can write, this winding configuration can be written as phi is equal to u times phi naught, where phi naught is some constant vector on this vacuum manifold, where u is some rotation field. Okay, u is some rotation field that takes you to this configuration. Actually, this rotation field is not completely specified, because rotations that leave phi naught unchanged. Well, if you have a rotation field, I can multiply by another rotation field on phi naught with a rotation in the z direction that leaves phi naught unchanged times your rotation field. So this is really valued in G mod h, but we don't have to get into all of that right now. Okay? Now, because this is the case, the gauge field what we need to do is to turn on a gauge field that undoes the derivatives of this part. But that, therefore, is a pure gauge configuration. Right? If we had a gauge field that was u del u inverse, then a gauge transformation of that, at least locally, will turn it to derivative of phi naught, which is 0. Is this clear? So because the vacuum manifold itself is generated by gauge transformations, the gauge field, the change in phi is that of a gauge transformation, and so can be brought to 0 along the angular directions by a gauge field that is pure gauge. And it's pure gauge with what? What u? Well, the u of this rotation. Is this right? Is this clear? So the gauge field we will need is an a mu, which is basically u inverse del u. Exactly. Yeah, exactly. What we have just shown really is that this S2 came about, this S2 vacuum manifold, okay, was the same as the manifold G mod H. So by this winding of S2 to S2, on one side of that you can think of it as winding of S2 at infinity to map a winding of G mod H, where G is the full gauge group, it's SU2, and U1 is mod H is the part that is unbroken. Okay, so this gauge thing will also have a winding, and gauge elements don't have windings on S2, because gauge group is S3, and there's no winding of S3 on S2. But G mod H elements, G mod H is S2. Wind on S2. Okay, so that's another way of saying it. Okay, so that's the kind of gauge field we'll need to turn on. The important thing here is because we're turning on a gauge field that is pure gauge, we will not at infinity get a field strength configured. That is the important point. Is this clear? Okay, so we can make the thing finite energy without getting this field strength contribution because we're turning on a gauge field that's pure gauge. Okay, now I want to say all of this a little more quantitatively and to show you that there is a connection between this winding and the magnetic monopole charge. That this is actually a magnetic monopole. I want to show you that. Okay, so let's do this a little more quantitatively. So let's see.
Only this subgroup is pure gauge.
What G mod X is, there is a gauge transformation. There's a map into gauge transformations.
If I look at mu, then subgroup of A.
First, G mod H is not a group. Okay, it's an equivalence class of groups. Okay, what all that is physical is G mod H, because H actions on the vacuum do nothing. Okay, so it's some element of this. This is the only physical thing. Okay, excellent. Now, let us somewhere here he has done this. Here. Okay, so let me write this down with sort of concrete equations. Okay, I'm using Harvey's notation, so we've got this d mu phi a which enters into the kinetic term of a Lagrangian. His notation is d mu phi a, and now we're using SU2, so and we're in the adjoint representation. So he has plus, very explicit, plus E epsilon ABC A B mu phi C. Is it clear that this is, up to signs and so on? Is it clear that this is correct definition of covariant derivative? Because this epsilon is the structure constant of SU2, and we're in the adjoint representation. Okay. Now, what we want to do is to take this guy and set it to 0 at infinity. Okay? So what we want to do is to take this guy and set it to 0 at infinity. So we just think of this as an equation that tells us what A mu is. Okay? How many equations do we have? Well, we have mu equations, D equations. How many variables we have? We have D variables. So you can think of this as an algebraic equation that will solve for mu. Okay? And doing this, he gets the solution. A mu is approximately because at infinity, minus 1 by E v squared epsilon A B C phi B del mu phi C plus 1 by V phi A mu. Let's call this A tilde. Okay. In getting the solution, Harvey has used that phi has modulus V square, but nothing else about it.
I think what I was saying is you have written A mu as U inverse del U.
Yes.
Now this will be in
the one which is in the direction of phi a, that can be anything.
That can be anything, correct.
Because that will not change.
That will not change it. That's exactly right. In fact, we're seeing that here. That's this A tilde.
That is the
A tilde here. Yeah. Okay, so just plug this back in here if you like. Use that phi squared is equal to v squared, and you'll find that this thing is 0. This is approximate because we've used phi square is equal to v square, but that's only true at infinity. Okay? Now, the nice thing about this very explicit solution, okay? The nice thing about this very explicit solution is now we can evaluate the field strength. Okay? Matter of simple computation. You evaluate the field strength. You find that this quantity here is phi a f mu nu divided by v. So the field strength in this infinite configuration is purely in the phi a direction. This we saw, right? That it was pure gauge, apart from, as Chintan said, anything you can do in the h direction, which is in the phi a direction. Okay? So, but you see this in equations if you do the evaluation. Okay? And this f mu nu, this coefficient of this thing, f mu nu is equal to minus 1 by e v cube epsilon a b c phi a del mu phi b del nu phi c plus f mu nu tilde. Is this clear? Okay? The important thing is, of course, you get this field strength that depends on what A tilde is doing. You don't know anything about it. But in addition, you get this thing. Okay. Now, this quantity, okay, this quantity on the other hand is proportional to the winding number of phi integrated on the sphere. It's basically proportional to the Jacobian of this S2 to S2 map. So when you integrate on the S2, you pick up the winding number. Okay, this is another thing one can, it's not hard to establish, maybe you already know this. We see this in many contexts, right? Okay, and therefore plugging in this explicit formula, we find the following. We find that integral B dot ds, where B is just the field strength of this quantity. It's this quantity. You know, this is purely spatial and we call it B. Epsilon ijk, Fijk is Bi. Integral B dot ds, okay, is equal to 1 over 2 e v cube times epsilon ijk epsilon abc del phi a del Hey, it's the thing that computes the winding, comes from here. So I'm just going to write it down. Where n is the number of times this phi map winds on the S2. Is this clear? Oh, okay? So what I wanted to show you was this thing that we've often said but never previously clearly demonstrated in class. Okay? That is that because the kinetic energy of this winding configuration has to vanish, because the kinetic energy of this winding configuration has to vanish, the gauge field is determined by the winding. Right? It's a pure gauge configuration determined by the winding. Therefore, okay, the field strength associated with this also determined by the winding. Okay? And that field strength then, this magnetic field, integrates at infinity to something finite. So the connection was we had to have zero kinetic energy that fixed the nature of the gauge field by this equation. When we computed the field strength and integrated at infinity. Now, maybe some of you are wondering, didn't we sort of, didn't we require that the field strength was zero? Wasn't this pure gauge configuration? So the field strength was zero. So how do we get a field strength? But remember that this is a very low field strength density. Because this field strength, F, has a finite integral around infinity. Okay? Therefore, the field strength goes like 1 over r square. This is that subleading piece of that F. It's the approach to zero. Okay? Which is captured in this charge.
Sorry, what about this F tilde?
And this F tilde just integrates to zero because it was just d mu. It's d mu a mu minus d mu a nu. And you're not allowing any. It's just a function. Here, these are now just functions. Okay? So it's there, whatever it is, but it integrates to zero. By Stokes theorem. Is this clear? Okay. So this quantity here is, this is the link between the winding number and the magnetic charge. This 4 pi by E is the statement that E times G is equal to 4 pi times N. This is Dirac's famous theorem. That electric and magnetic charges, the product of electric and magnetic charges, quantized in units of the sum h bar if you keep things properly. Okay? Great. So this configuration here, whatever it is a monopole. So far, however, we've been extremely abstract. At least in the one monopole sector, it would be nice if we could find the solution explicitly. All we know about the solution is that it winds at infinity, the gauge field does something infinity. What about at zero? What happens there? Okay? Now, in general, finding the solution to these equations is a pain and depends on the nature of the potential. Okay? But there is a special case in which solutions can be found very easily. And as you might expect, that special case is what applies to us. Namely, it's the supersymmetry case. So I'm going to tell you about it.
Doesn't the kinetic term for F diverge logarithmically?
No.
F goes like 1 over r square.
F goes like 1 over r square, and we have d3r.
So F square is 1 over r to the
Fourth, and we have r squared dr. Yeah. Had we been one higher dimension, it would have been what you're saying. Right? If you remember, the kinetic term naively went like linear divergence. What we are doing is making everything go 1 power of r lower. So instead of d mu phi going like 1 over r, d mu phi goes like 1 over r square. Also the f's. Okay? And therefore, that linear divergence is turned into a linear convergence. It's 2 powers of r in square. Okay? Excellent. Other questions, comments? Perfect. Okay. So, now what we're going to do is to try to see some interesting structure of these equations, the equations that actually determine the solutions of this monopole. In the special case that something special happens, actually, that the potential vanishes, as I will explain. Okay? And our analysis goes as follows. Okay. First, let us notice this thing. The magnetic charge of our monopole, which by definition was this B dot ds, which is the same thing as, again by definition, phi a by v b a dot ds. That was here. That's what our b was. Okay. Phi a dot b dot ds. Okay. This now on this object we use Stokes, whatever, Stokes, Gauss, whatever, that theorem that relates surface terms to bulk terms. Okay? So this quantity now we can replace by the bulk divergence, bulk integral of the bulk divergence of this. Okay? So there's a mu here. So this is d mu phi a b mu a integrated over the volume d3x. Right? Surface integral is a volume integral of a divergence. But now we use a trick that's often very useful. On a singlet, when acting on a singlet, a normal derivative is the same as a gauge derivative, the gauge covariant derivative. Okay? So we can replace this d mu by capital D mu. And so every time I write mu, I should be writing I. Everything is space. Okay? There's no time in the whole game. I apologize for that. You understand, right? Okay. Now, and then we use the Leibniz rule. Okay. So we use 1 by v integral d mu phi a dot ba mu plus phi a d mu b mu a d3x. But d mu b mu a vanishes as a consequence of the whatever identities, Bianchi identity. Okay? This you're familiar with, right? In the abelian theory, you know it, and it's also true in the non-abelian theory if you change d mu, ordinary derivative, to covariant derivative.
That's full space-time derivative.
Full space-time derivative, but everything that would not appear here is 0 in the solution. A0 is 0, del 0 is 0. So you can make it the full space-time thing because we're just turning on the static solutions. Okay? So this guy is 0. So now we've got a nice representation of this G as 1 by v times integral d mu phi a dot b a mu. Is this clear? Okay. Now, keep this equation aside, let's call it 1, and let's look at the energy of our solution. The energy of our solution was d mu phi, the whole thing squared, plus b squared, b mu, where I'm using the fact that the stress tensor of Yang-Mills theory is E squared plus B squared. I mean, the energy density of Yang-Mills theory is E squared plus B squared, and of course this d mu phi square will come from the kinetic part of there's no time in any of this, so it's all easy. Okay, everything's I here. Okay. But notice that this and this are the two terms that appear here. Okay? And so what we can do is to write this as d mu phi plus b mu, the whole thing square, minus minus b mu square plus 2 integral. So actually the energy has a half, right? Because kinetic term for a real scalar field has half. So this is half, and there's no 2, and there's an integral b dot d mu phi. Okay, but this quantity was equal to v times g. Okay, and so we find that the energy of our solution is equal to half of d mu phi a minus b, the whole thing squared, plus v times g. Now G contains in it the information of how much winding we had, or what our magnetic charge was. So in a configuration with a given magnetic charge, equivalently given winding number, V times G is some fixed number. Okay? So clearly the energy of such a configuration is bounded from below. Oh, and something else I forgot through all of this. The energy was this plus V of phi. Yeah. Also there's the bare potential energy. So with that, this is clearly greater than or equal to 0. Now, in some reasonable configuration, V of phi may vanish at infinity, but won't vanish near 0. Phi is doing something strange near 0. For instance, if we have this Mexican phi to the 4 kind of potential, our solutions will be of the sort that at 0 are near the minimum, at 0 at the maximum, but at infinity go to the minimum. So V won't vanish everywhere. So this bound here, we're assuming V is a positive number. Okay? That's why we get greater than or equal to 0. So this bound here is impossible to, saturate if V of phi is a non-trivial function. Okay? If we look for solutions that saturate this bound, we need two things. We need louder, sorry. Yeah. If we had minus G, I would have done this thing with a plus here. Right? So right? So V of phi. What? V of phi is required to be positive everywhere. You see, of course, positive is just a matter of subtracting the vacuum energy. So V of phi is some function. At its minimum point, whatever that is where the vacuum sits. Okay? If that energy wasn't positive, we'll subtract it away. This is just quantum field theory. There's no meaning to that overall energy. So when I say positive, I just mean that everywhere V has value larger than its vacuum value. Well, that's all that matters. Vacuum is what is reached at infinity. So you may think it's odd to have this positivity requirement, but that's all we mean. So the vacuum is the lowest energy configuration on the same. Okay? So this V of phi here, okay, needs to be 0. Suppose this is equal to 0. Then in order to saturate this inequality, all we need is the condition that d mu phi A is equal to B. If we can find such a solution to this equation, okay, if we can find a solution to this equation, many things will happen. A, solving this equation guarantees that we solve the equations of motion. We can check that algebraically, but it's even clearer logically. It's even clearer logically because the equation of motion, this is the configuration of lowest possible energy in this charge sector. So clearly it has to solve the equation of motion in the stationary way. Okay? So notice that this equation here is a first order equation rather than the equations of motion which were second order. This is huge simplification. And in fact, as you know, there will be another way to get this equation in the theories we're interested in, namely it will be the equation that emerges from supersymmetry. So this equation will be the equation that guarantees that the monopole is supersymmetric. We've not yet introduced that. Right now we're just being crude. But as you know, this is how it's going to work. Is this clear? Okay. So this equation was what was originally called the BPS equation. Bogon, Molny, Prasad, Sommerfeld. And this bound, so what was originally called the BPS bound, supersymmetry has inherited that name. Okay, and taken it to more general situations. Okay, and was derived like I've told you about. It's not by using supersymmetry, just simple manipulations of classical equations. Is this clear? Okay. Now, if we require, now, I'm going to talk about how you can actually solve these equations. Okay? Look, in this nice scalar theory, in the n equals 1 sector, we can look for a lump. It's very natural to look for a lump that is spherically symmetric. Except, because it's very natural to want a solution that has spin 0. Right? We're looking at our theory preserves rotational invariance. We're looking at a solution. It's natural to want that. However, you might think this is completely impossible because we've said that different things happen at different places. Okay? That if something is spherically symmetric, what's happening here should be the same as what's happening here. But at this point, you're pointing in one direction in group space. At this point, phi is pointing in another direction in group space. So it's not spherically symmetric. However, what we mean by spherical symmetry has to be examined. Okay? So let's look. You know, we had this gauge group which was SU2. Okay? And we have space of rotations in three-dimensional space which is also SU2. Okay? Now, our field configuration phi transforms under both SU2s. One SU2 rotates it because it rotates the positions inside your configuration. And the other SU2 rotates it because phi was an adjoint field under this SU2. So, if you can manage to get one of these to cancel each other, that is, if you can try to search for a configuration that is not invariant under either of these two SU2s, because we know it won't be, right? We know it can't be invariant with gauge SU2 because phi has a certain magnitude. There's no field phi that is invariant with a certain magnitude that's invariant under that gauge SU2. Take any vector, rotate it, go somewhere. Okay, we know it can't be invariant under that. We know it can't be invariant under rotations because of what we said. We want winding. It's impossible for that to be, invariant under. But you see, the way that it was not invariant under rotations was a bit fake. Because we said it's pointing this way in group space here and that way in group space there. But all directions in group space are basically the same. Okay? How do we make that mathematically precise?
So what are we trying to achieve?
We're trying to find a solution which preserves a rotational invariance. Okay?
Not the full SU2 plus SU2, but some.
We want to find something that preserves rotations. I mean, spatial rotations. So just one SU2. Okay? We're trying to define what that means. Okay? So suppose we do simultaneous rotations. This diagonal subgroup where we rotate here and here equally. Then it sounds reasonable that we'll be able to find such a solution. Okay? So now let's try to write down an ansatz that will have that feature. Okay. So let's try to write down an ansatz that will have that feature. Okay. And This one doesn't. Let's take phi A to be r hat A by ER times H of R, but for convenience we write it as EVR. And AAI is equal to epsilon Aij R hat j by ER times 1 minus K of EVR. What? We'll see what H and K are. At the moment, they're just any arbitrary functions. They'll be even simpler than Bessel. Okay? We don't know what they are, but they're functions only of radius. That's the important point. Right? Spherical symmetry buys us that. Right? If you have a spherically symmetric solution, everything's a function of only one variable, so you can actually practically solve. Okay? Notice that what we've done is murder here. R hat had a space-time index. We've identified the gauge index here with the space-time index here. This makes it clear that the solution doesn't preserve either of the two SU2s alone. But it also makes it clear that it preserves the combined SU2. If A transforms the same way as vectors in space transform, then this thing preserves that SU2. Okay? That's clear. Okay. Excellent. Now, this is our ansatz. We take this ansatz and plug it into here. And we get some equations for these two unknown functions, H and K. Okay? Matter of simple algebra to do that. The equations that come out are the following. Minus. You get y k prime is equal to minus kh, and y h prime is equal to h minus k square minus 1. Okay, just a matter of plugging in and checking. Is this okay? Okay. The reason we have two equations is that when you plug in, what we will get is equations with two index structures. One will be an RA and the other will involve an epsilon. Equating the coefficients of each of these index structures will give you the two equations. Okay. Now these are ordinary differential equations of functions with one variable. Okay, and you might suspect that you can solve them, and you can if you work hard enough. And the solutions are remarkably simple. Solutions are h of y is equal to y cot hy minus 1, and k of y is equal to y by sin hy. Okay. So in the case that we're looking for this simple single solution, one monopole solution, preserving spherical symmetry, and setting V equals 0. We have a very simple and explicit solution for this monopole.
Here AR is 0 in this solution.
A what? I's, all SO3 labels are here. These are X, Y, and Z. That's why there's an epsilon ijk. IJA. These are just Cartesian coordinates. Right? Now, A will have the property that it will be essentially in the angular directions. But the solution here is complete. Okay, excellent, excellent, excellent. Yeah, the fact that A is in the angular directions follows from the fact that you're dotting this index with r hat. So A's non-zero components are in the angular direction. Okay. One or two things about the solution. Okay. One or two things about the, yeah, go on. Sorry. But yeah, just plug that ansatz into the boxed equation. Oh, sorry. So from the boxed equation, just solve it. There are, but you demand conditions at infinity. No, del mu phi equals 0 is done. But you demand that your fields die off at infinity. Okay? So, right. So, you demand that, yeah, okay, what are the, under what boundary conditions do you solve this? You solve this, we want that phi A, we want that it reaches V r hat A at infinity. Okay? And yeah, I suppose that would fix everything. Okay. What?
The gauge field A would go to 0.
A will go to 0 at infinity. Yes, A will also go to 0 at infinity. Go like 1 by r. You would demand.
The d mu phi equal to 0 using which we solved A.
Yes.
That should also be satisfied. That is automatic.
That was this. D mu phi equal to B, BA, that one?
This condition where we solved d mu phi.
You see, both of these, right. Because this phi A goes to RA at infinity, this d mu phi A will go to 0 at infinity. All of these, yeah, exactly. These are equivalent ways of saying it, right? You want this d mu phi A to go like 1 by r square. Okay, exactly. It's that condition. That condition that the thing decays fast enough to the vacuum manifold, and its derivatives, right, are 0. Okay, yeah. So putting in this condition gives you a unique solution. Okay, excellent. So now we have there are two integration constants. Yeah. Let's see. We can try to put. If you're uncomfortable, we can. I would have to do it. But would you like to try to do it? Yeah. Yeah. This is. I think that it goes to 0 fast enough. That both of them go to 0 fast enough. Is just complete. What? A goes to 0 is another condition. Of course, A is determined by, its field strength is determined by, yeah, maybe there's some gauge.
A tilde field is more.
A tilde field, will be set to 0 by that equation, right? Because that is telling us the full B in terms of d mu phi. You see, turning on that A tilde gives you more energy. You don't want that, right? Yeah, I would have to check to see exactly how it works. But I think basically the fact that things go to 0 fast enough at infinity is enough to completely determine all solutions. Okay. Okay, excellent. There are one or two things that I wanted to say about this, about the solution before we moved on. Okay? The first thing I want to say about the solution is let's look at how phi behaves at infinity. Okay? So phi is given by this. So phi goes like h, it goes like 1 by r, or phi goes like 1 by r times h. times h. And h goes like, this is r, and h goes like, so let's talk about it in terms of y. Y is this rescaled r variable, ERV is y. So phi goes like 1 by y times h of y, which goes like cot hy minus 1. Right? Now, let's look at cot hy. Cot hy goes like, is equal to e to the power y plus e to the power minus y divided by e to the power y minus e to the power minus y, cos h divided by sin h, which is equal to 1 plus e to the power minus 2y divided by 1 minus e to the power minus 2y. Okay? So which is approximately equal to 1 plus 2 e to the power minus 2y. And so cot hy, so it looks like, have I got this right? H of y goes like e to the power minus 2y. That looks funny. Just give me a minute. It was y was multiplying only cot. Sorry, I wrote this wrong. Y cot hy minus 1. This is the solution. Okay, so let's do this again. So this is minus 1 by y. Okay. Goes to 1 with these exponential corrections. Okay. So we have that this phi goes like 1 minus 1 by y plus exponential corrections. Okay? Now, in a theory where you had a massive phi field, you would expect the approach to this manifold to be exponential because the theory has a mass gap. Okay? And that's sort of what this cot h is depicting here. This part. Sorry, where were we? This part. But there's also this 1 by y. Okay? And this 1 by y is telling you that it's not approaching the vacuum manifold. The modulus of y is not approaching v exponentially, basically because we've insisted that this theory has no potential. Okay? So in a theory with no potential, the approach to the vacuum manifold is, of course, only power law. What else could it have been? Oh, what could set, the scale, otherwise. You would expect it to be just only power law. Okay? Now, this brings us to an odd thing here. We started our whole discussion of this solution by saying that there is this vacuum manifold picked out by the potential. Phi was forced to have some length v that was picked out by the potential. And now we've gone to have a case where there's no potential. So you might wonder, does the whole discussion apply? And it does. It does, though delicately. It does because of spontaneous symmetry breaking. You see, in a theory where there is no potential, fields at infinity don't fluctuate in higher than, 2 dimensions. And 3 and higher dimensions. Fields at infinity don't fluctuate. This is spontaneous symmetry breaking. Okay? Now, spontaneous symmetry breaking tells us that up to gauge transformations. Therefore, phi at infinity, you can choose it to be whatever value you like, but will not fluctuate. So at infinity, we're going to have the same value up to gauge transformations. Okay? So V is fixed by the spontaneous, by this infinite action of change of vacuum in high energies, high dimensions. But it's fixed only very weakly. And that's why we have this power law approach to this V. Okay? This is related to the following fact, that the Higgs field in this theory. See, once you take this theory and you Higgs it. You go to its, you do the spontaneous symmetry breaking, you Higgs your gauge field. What is the spectrum of particles in your theory? Well, the Higgs field, the angular direction of the scalar field is eaten up to give the W bosons a mass. But the radial direction of the Higgs field continues to be a physical fluctuation, as you can see by going to radial gauge. Okay? In a theory with a potential, that is a massed up physical degree of freedom. But in a theory with no potential, that's a massless physical degree of freedom. So our theory now, our theory, even in the vacuum, had massive W bosons, massless phi field, massless AMUs, the U1 gauge bosons that we had, but also a massless scalar field. Okay? And this tail here, that 1 by r, is a consequence of there being this massless scalar field. Okay? This massless scalar field is going to play a big role in what we do going ahead. But let me tell you that immediately. In a theory without this kind of massless scalar field, okay, if you try to put two solitons together, since they have equal charge, they would repel each other. Okay? So these solutions would not exist. They would just move off to infinity. However, in addition to this, there is also the force of exchange because of the massless scalar. And that massless scalar tends to attract. And in these theories, that repulsion and attraction exactly cancels. And this is why you have non-trivial solutions involving more than one soliton. Okay? We will come back to this as we proceed with analysis. Okay? This is very similar to situations, things we see with D-branes in supersymmetry theories. It's always multi-D-brane configurations are stable because something cancels something else. Okay? Or in that context, it's often gravitational attraction, but also dilaton attraction, cancelling gauge repulsion. Okay? Clear? Okay, excellent. Fine. So now, at least in this supersymmetric situation, at least in the situation where V is equal to 0. By the way, why is V effectively equal to 0 in n equals 4 Yang-Mills here? We're doing all this so that we can understand n equals 4 Yang-Mills. So let's go back to that and try to ask, why is V effectively 0? You remember what V was? V was phi I commutator phi j, the whole thing squared. Didn't look like 0. But the point is that what we're going to do is to turn on only one phi I. We separate the brane in one direction. We've got two branes and they're separated in some direction. Okay? So our whole solution will be with just one phi I turned on. And there's no potential for one phi I. It's potential that involves non-commuting phi fields. So effectively in n equals 4 Yang-Mills, we separate in one direction. V is 0. Okay, that's why this analysis applies to that case. Is this clear? Okay, there were 6 scalar fields, we turn only one of them on. Our solution turns only one of them on. Doesn't matter which linear combination, but only one linear combination. And that gives us effectively 0 potential. That's why it applies to that case. Okay, excellent. So, now we have very complete understanding of this solitonic solution. Just to summarize, it's this lump with winding, also lumped with B field. It's centered around here. It's nice and spherically symmetric when thought of appropriately. Okay, great. Now, Now that we've got this one solution, you can ask, do we have other solutions to the problem? Okay? Clearly, you can make other solutions by taking the soliton, which was at the origin, and moving it. Just acting with translations on the solution will give you another solution. So we've got a 3-parameter set of solutions. Okay? That's interesting, but there's something more interesting, which is, now that we've got this 3-parameter set of solutions, we can make this solid, we can also boost the soliton. Okay? Boosting the soliton will make it move. Okay? One way to generate the boosted solution, and all its properties, of course, is just by boosting, just by using Lorentz transformations. But there's another way of doing it that is sort of educative, and that will extend to more general things. To extend to, let's say, the multi-monopole configurations, where you won't be able to generate all configurations so easily. And that is to think of this through collective coordinate quantization. Okay? So what do I mean by that? Let's say I've got my soliton solution here. This solution I think of as being S, which is a monopole located at some point, let's call it R0. In our discussion, we've chosen R0 equals 0, it's the origin. But of course, by translations, we could choose any R0. Okay? Now, what you can try to do is to ask this. Suppose I look at configurations which are of this form. My solution, so S is the solution, it's phi and A and everything. Suppose I look for configurations in which this solution here, okay, is simply R0 as a function of time. I want to search for such solutions in my theory. Okay? You see, if I keep this time variation very slow, then this should accurately give me the lowest energy configurations of our theory. Right? Because when the time variation goes to 0, these are exact solutions. Okay? So we could look for slow time variations of this, and basically the solutions we should be that will come out of taking this R, putting it in here, in the action, and quantizing the theory, will essentially be solutions which set the soliton moving. Okay? And we're going to go through that in a minute. But now that we've thought of this, there is something else we could do.
But all this is a spherically symmetric system.
See, there is the set of static solutions of this theory are very few. There are these spherically symmetric solutions, and then you can translate them anyway. Also, you can do a gauge rotation. We'll come to that. Okay? But what we are now trying to do is to take this thing thought of as an object and look at its motions. Of course, once it moves, it's not spherically symmetric anymore. But it's motion of a spherically symmetric object. Is that what your question was?
But even at the static level, there are no more solutions.
There are no more solutions. There are no more. Okay, good. Certainly, there are no more BPS solutions because we've just derived it and found all. Okay. Now you could ask: are there additional solutions to the equations of motion that are not BPS?
Even the BPS U2 can answer that SU2.
Are there BPS solutions that are not spherically symmetric? I think the answer is no. Yeah. The set of all BPS solutions are the ones we found. In fact, there's a sort of index theorem that counts these solutions. And with the appropriate way of saying it, there are 4-parameter set of solutions. And we'll find them all just now. Yeah, so no. Okay. Yeah. So now, we can answer that immediately physically. Because the energy now will not be mass, it will be square root of m square plus p square. So its energy will increase. but increase in only a very, in a limited way. In the sense that all of these configurations can be made arbitrarily near these BPS configurations. Right? In fact, the guys that are just moving will themselves be BPS, but in a slightly different way. Let's come back to that in 2 minutes. We will see this. You will see this. Okay, physically you can see this, right? Because since boosts are a symmetry of the theory, if you boost a supersymmetric solution, it will stay supersymmetric. But it doesn't preserve which supersymmetry it's supersymmetric under. Okay, so that's all that will really happen to the final solutions of these theories. But and it's a bit more complicated in the dione sector. We'll come to that.
And any or not, I suppose R naught is a function of t.
Yes.
I'm looking at some non-particular value of t.
Yes.
At that particular value of t, the static solution will always be whatever R naught it is there.
Yes, it's always a solution.
It's always a solution and it's a minimum energy configuration.
Yes.
But then if R naught of t has a non-zero derivative,
Yes.
then shouldn't that increase the energy a bit?
It will. So now we will not get minimum energy solutions anymore. It will be, the final solutions will be square root of, energy will be square root of p square plus m square. Right? It's exactly the same situation when you're doing quantum mechanics of a particle. Minimum energy solutions, the particle sitting at rest.
But for this still to be a solution, there should be some condition on low variation.
Of slow variation. In fact, because we're doing such trivial things here, we can get a solution more generally, just by boosting, right? Without any condition. Okay? But the method of analysis I'm using assumes this. And its utility will be that it will apply for 2 more complicated situations where it's not just generated by symmetry. Right? But for actually what we're doing, it's clear beforehand that it's a solution.
So in this method, we will get non-relativistic quantum.
Exactly. We'll get non-relativistic quantum mechanics. Exactly. So, now, in sort of partly to address all the questions that have come up, including Diksha's, let's look for this collective coordinate kind of thing. Okay. The first thing we do is we have to understand what these collective coordinates are. We've already written down 3 of them, just moving the solid. Those are obvious collective coordinates. Question is there any other? Okay? And now we're going to do this thing which is sort of very irritating when you're working at the level of the unmoved thing. You're never clear whether you should think of it as a new solution or not. But when you actually start moving it, it'll become very clear. And what we're going to do is to do a gauge transformation. Okay? In my experience in this game, once you know the answer, you give grand words. These are large gauge transformations because of blah, 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 blah. I never believe all that stuff. Okay, it's really concretely clear if a solution that you're working with is not gauge equivalent to another solution. That's clearly a new solution. If you're going to use some configurations along the way that happen to be gauge equivalent as a tool in constructing these solutions, great. Go ahead. If you're going to get things that are gauge equivalent, you better have some good physical reason to believe that they're new solutions. There's a lot of discussion about this. I don't know, it always gives me a headache, and maybe it's my limitation, but I always am very suspicious about all these large gauge transformations. Okay? But just to say it often gives you great physics. But I don't know, it always makes me uncomfortable. Okay. Okay. So here what at the practical level, what we are going to do is use these large gauge transformations as an intermediate step. Okay. And that Do you have something here?
This one thing, what time will you be finishing up?
About 1:30. Yeah. Okay, so we're going to use these large gauge transformations as an intermediate step. So what we're going to do is this. We had this solution, right? And what we're going to do is to take the solution and do the following to it. Okay, so I'm going to find my fourth static solution. That's what I'm trying to do. The three static solutions we've got, 3 parameter set of static solutions we've got, just by moving R naught, without any T right now. Okay, my fourth static solution, what I'm going to do is to take take phi and take phi and make it chi of t times phi. It's chi, constant chi times phi. And in this situation, just a minute. Okay, let's first do the algebra, then we'll figure out what it means. Just take phi and make it chi times phi, where chi at the moment is just some number. Okay, we will come back to what it means in 1 minute. Okay. First, I want to check that this continues to be a solution. Okay, so chi is just a number. So what I'm trying to find is, I'm trying to find an infinitesimally deformed solution. Okay, so I'm taking phi is equal to phi plus chi phi. This will in the end be just some sort of gauge rotation. That's fine. Okay, we'll examine what it means in 1 minute. Right now, I'm looking for this solution. I'm going to try to show you that there is a solution to the BPS equations. Okay, that there is a solution to the BPS equation. That given a solution, that my original guy solves the BPS equations. This new infinitesimal deformation also solves the BPS equations. Okay, where chi is just some number. If it will have to be a phase in the end. But right now, just for the algebra, it's just a number. Okay, what do I have to check? I have to check that it solves the BPS equation. I have to check that this new phi continues to solve del mu phi A is equal to BA. Okay? And also that the Gauss law constraint equation d mu f mu nu is equal to j mu continues to be solved. This will become more non-trivial when we take time dependence in a minute. Okay. Now, this equation, we take this condition, plug it into here, and linearize. Okay? that linearization gives us the following equation. Epsilon ijk del j delta ak, okay, epsilon ijk del j delta ak is equal to di delta phi plus delta a phi. Okay, so this we put in here, and the Gauss law equation is di delta ai dot plus phi dot equals 0. Right now we're looking for static solutions. Since these equations have dots in them, they're trivial. Okay, let's focus on this equation. This equation should also have a first order term. What do you mean a first order term? Yes, everything here. Yeah, thank you. Yes, one of them. This is delta phi dot. Thank you. Yeah. Okay. Now, let us look at the following thing. Let us look at delta ai equals del di of chi of t times phi, and delta at the moment static. I'm writing t, will take static in just 1 minute. Delta phi equals 0. Yes, actually I wrote this. This was abstract. Ignore this, sorry. This is the solution we're going to look at. Okay, great. Yeah, it's making sense now. Suppose I look at such a configuration. Let me first plug it in when nothing is a function of time. Okay, nothing is a function of time, so this guy is clearly satisfied. Okay, now this guy here, because it's not a function of time, okay, is di of phi. Okay, and so we get, why is it satisfied? Just one. This is satisfied for the following reason. Just one second. It gives you the field strength. Gives you the field strength, and on the right we get di phi. Yeah, and the field strength was itself B, right from there. Was itself di phi. Yeah, so that's why it's satisfying. So at least roughly, let's see how this works. Okay, so put everything independent of time and plug that in here. So as you guys said, this is epsilon ijk dj dk of chi times phi. So chi is just overall outside. dj dk of phi. Okay, but because epsilon is commutator, that makes it ij commutator. Ij is what we called bi. Okay. Okay, so this is sort of bi phi. And b we replace by del mu phi. So this is sort of like del I phi phi. Okay. On the other hand, here in this term we have, okay, and let's be a bit careful so that delta A, so delta A was taken to be this phi, yeah, perfect. So in this term here we have delta phi, but that's just 0. Okay, and in this term here we have delta A commutator phi. Okay, but delta A was di phi, so it's di phi commutator phi, and here also there was a commutator, right? Because this, because we want, yeah, why was that a commutator? It was because in this term, how did it go? This was dj. Right. It was, we had this, we had dj on phi, but this is exactly, because it's the adjoint representation. So it was that commutator phi. You plug it in, you get the signs right, they cancel each other. Okay? So at the algebraic level, we see that we have these new static solutions. These new static solutions in which phi is not changing, but A has been changed by this quantity which is di chi phi. Now let us interpret this algebra. This is a change in A like this is exactly what is generated by gauge transformation. A gauge transformation with a gauge parameter which is chi times phi. Okay? Now precisely because the gauge transformation is in the phi direction, phi does not change because phi is the adjoint representation, so it changes by commutator. Okay, so gauge transformation, which is generated by this infinitesimal quantity chi times phi. A gauge transformation generated by the infinitesimal quantity chi times phi is what we've just done here. Okay, so we knew beforehand that of course everything would be satisfied because it was a gauge transformation. Okay? And so this is one of those situations where you don't know if you're just fooling around and, wasting a lot of time doing nothing.
Sorry, how do you know that this is a new solution? It's not equivalent.
Exactly. How do you know that this is a new solution? Maybe, maybe not. Who knows, right? This is one of these situations that Harvey has a lot of words about large gauge transformations. Okay, I never trust that. Okay. However, in what we're going to use it for, it'll be clear that it's new. Okay. What we're now going to do is like what we do for the translations, is we're now going to make chi a function of time. Notice in this we will not turn A0 on. Okay? Delta A0 is equal to 0. All we're doing is taking this thing that was clearly a solution, static solution, and making chi a function of time. Had we turned A0 on in the way to make it a gauge transformation, it would obviously be a solution, it would be a gauge transformation of the original thing. And then we could ask Diksha's question, how do we know that it's a new thing? And I would give the answer, I don't know whether it's a new thing or not. Okay. However, now what we're doing is not gauge equivalent to the original thing. Okay? We're just taking this set of configurations that were definitely solutions to the equation, whether or not they were pure gauge, and making a parameter in that a function of time. But once it becomes a function of time, it's not pure gauge anymore. So it's definitely a new solution. Okay? And it also lies in the low energy sector, just like these translations. Because when you make it independent of time, it will obey the equations of motion. Okay? So this will be some slowly varying kind of thing. Is this clear, Diksha? Okay. Now, so this is a set of configurations we've got. We've got these configurations labeled by this chi of t, this gauge transformation, which is a function of time, except it's not quite a gauge transformation. Because we're not turning A0 on. This is really important. Okay, it's going to a genuinely new configuration. We'll have different energy.
Like for the case of translation,
Yes.
we use Lorentz transformation to get these new configurations which are not slowly moving.
Yes.
Here, what is that?
Yeah. Here, what is the analog of that? Okay. What we will see is that this will generate charge. Okay. And at least in the supersymmetric theory, we will find a new BPS bound, which this solution will exactly saturate. So BPS protection is one answer to your question. Okay, it's a bit hard to get, in some situations. In some situations, we can get the answer to your question more geometrically. Let me give you 1 minute on that. Are you guys familiar with Kaluza-Klein theory? Okay. You take gravity theory and put it on a circle, and you generate gauge fields because of translations in that circle direction. Diffeomorphisms on that circle direction were these gauge transformations. Now, to turn on charge is to set something moving in the circle direction. Okay, to give it a momentum in the circle direction. In that situation, turning on this charge is boosting in that extra direction. Very much like what we do in the other directions. The only difference is that it's boosting in the direction of the circle. In such a situation, this is one of Maldasena's, he loves doing this. In such a situation, you can generate exact new solutions by doing this boosting. In a situation where there is no dilaton field, but in some contexts, you can do very classically, explicitly what you want. Okay, and in that context, it's basically because it was also a boost, broken by something, but you can deal with that. Okay, but in the general context, supersymmetry is what protects the existence of such a state. But to find it classically will be difficult. Also, it's not even clear that you should be able to find it classically. Is this clear? Okay, excellent. So now what are we going to do? Now that we've got these collective coordinates, okay, what we do is just plug this configuration into the action. Okay? Just plug the configurations into the action. Now, something sort of nice happens here. Because you see, whether or not these things were time dependent, these configurations obeyed the BPS equations. See, the BPS equations only had space derivatives. It didn't care if something was a function of time. Okay? And so, most of the action is sort of, what is it, E square minus B square plus kinetic term square. Now split that, take the part that's B square plus spatial kinetic part. That's exactly what appears in the energy. And that, by the BPS argument, becomes E times G. So the only part of the action we have to worry about are the kinetic terms. That is the E square and the time derivative square. Right? So all we need to do is to take this configuration and plug it into that. Okay? Now, when we do that, we're going to get some, so let's call the collective coordinates whatever they are. What?
Are there no collective coordinates?
No, not. The size is something that's going to be, it is just fixed. See, for instance, our solution gives us a particular size, set by E times V. There's a vacuum expectation value at infinity that breaks scale invariance. And therefore, you get a monopole of a given size fixed by that scale. You could get a collective coordinate in that sense. You could scale the whole thing up, but then you're changing the vacuum expectation value at infinity. And that's a solution in another theory. That's not finite energy. Okay, excellent question. If you could try to put that into the action and see. You could just take lambda, scale the whole thing up by lambda and try to make it lambda as a function of time. That will be infinite energy. Very much like we saw some things in this Witten story that we were analyzing. You remember we saw some things for infinite energy, right? It's very much like that. Okay, it's just spontaneous symmetry breaking. Okay, great. Okay, so, we'll have to soon stop since they seem to need the room, but let's quickly say this. So what we do is to take these configurations and plug it into the action. We only need to plug it into, E square plus del 0 phi, the whole thing square. Plug it into here, and when you do that, you get do the integrals of a space. You get some g alpha beta r alpha dot r beta dot integral dt. Okay? So you've got some effective theory of quantum mechanics of these collective coordinates. Okay? Next class we will talk a little bit more about the explicit form of this G alpha beta, this metric on moduli space. Okay? But as you can imagine, the metric on moduli space is flat in the three directions. Because it's just the metric for motions. It's a metric on R3. And it's a circle in the circle direction. Why is it a circle? This is very important. Why is it a circle? Because you see this chi was a periodic field. Okay? That when you do this transformation of chi, when you do it with chi here was coming from expanding an exponential. What we're doing is e to the power I alpha on phi. It's coming from that. Okay? Now this alpha there is therefore a periodic coordinate. Because it takes you back, because the gauge group had this periodicity in it. You do a gauge transformation by something, or you do a gauge transformation by something after a 2 pi rotation, it's the same gauge transformation, same group element. Okay, so on the space of static configurations, whether or not you believe them to be physically different, certainly if you do a 2 pi rotation, it's the same. No doubt about that, right? Okay, so when you take this thing, the metric on moduli space we will get will be metric on flat space, R3, times a circle. The coefficients behind these will be different. We'll see this. Okay? Now when you quantize, what do you get? Now we just got quantum mechanics of a particle moving in R3 times a circle. Okay? And the states are labeled by momenta in R3, that we always knew, but by an integer on the circle, the Kaluza-Klein momentum on the circle. Okay? And that integer on the circle, is going to be the charge, the electric charge associated with the solid. We will see this all in a little more detail next time. Okay? So this collective coordinate method helps us explicitly construct the Dionic solutions around this solid. In a little more detail we will see this next time. Also discuss the BPS bound on these solutions. Yes?
If this gauge transformation chi of t was not in the direction of phi,
yes,
that is not a solution?
If the gauge transformation, no, it is a solution, but go on.
It's still a time derivative and I do not change delta is 0.
Yeah. But what you're doing is changing the vacuum at infinity. See, so phis are changing. You want to keep those phis what they are, not change infinity. So the thing is that kind of configuration, if you did what you are saying and made it a function of time, you'll get infinite energy. Why?
Sorry, what is the gauge transformation?
Chintan is looking for a gauge transformation that is not in the 3 direction, but rotates on the sphere. Rotates on. So Imagine that we've got a local phi direction here. We've got one gauge transformation along this axis, but another kind of gauge transformation that rotates this axis. So this is the thing that will change the direction of phi in time. So Chintan's asking, what about that kind of gauge transformation? If I perform it and it's static,
Delta phi is not 0.
delta phi would not be 0. Exactly. I perform it and it's static, it would definitely be a solution, no doubt about it, because it's a gauge transform. Important question is what happens when you make it a function of time? That will now gain infinite energy. Because you will be doing these rotations in this time dependent way without compensating for them by an A0. And this is exactly like the beginning of this lecture, right? You can't move things at infinity unless you do it in a pure gauge way. Okay? So it was really important that the gauge transformation we did was in the phi direction. So as to get a finite, this metric on moduli space has to be finite. That's another way of saying it. You can do whatever you want, but in the end you should get a finite metric on moduli space. Okay? Let's stop here and continue next class.